Hey, this is Kyle, and I'm going to be talking about the Lewis relation, and that's part A1 of exam 3. So if we remember from our last exam, we were discussing the Sherwood number, and we found this relationship A times Reynolds to the B times Schmidt to the C. And Sherwood number itself is defined as the mass transfer coefficient times the distance d over the mass diffusivity dAV. And then I'm also going to want to take a look at Nusselt number. So Nusselt number is defined as the heat transfer coefficient times the distance d over the thermal conductivity. And if we do the same experiment as we did to find this relationship, we find a similar relationship of Nusselt number being equal to A times Reynolds to the B times Prandtl to the C. And these A, B, and C, these constants are actually the same. So now I want to take a look at Sherwood over Nusselt. So A and Reynolds to the B are going to cancel. So we're left with Schmidt number over Prandtl number to the C power. Well, Schmidt number over Prandtl number is defined as the Lewis number, so Lewis C. I also want to do this calculation with what these are defined to be. So that's going to be equal to the mass transfer coefficient times the distance d over the mass diffusivity times the times the reciprocal of the Nusselt number, because that's the same as division. So we're going to multiply by the thermal conductivity over heat transfer coefficient times the distance d. So this distance d is going to cancel out, and we're left with this equation. So now I want to take a look at the Schmidt and the Prandtl number. So the Schmidt number is equal to the kinematic viscosity over the mass diffusivity, and the Prandtl number is equal to the kinematic viscosity over thermal diffusivity. And I want to do the same thing, Schmidt over Prandtl. So Schmidt over Prandtl, the kinematic viscosity will cancel out, and we'll be left with thermal diffusivity over mass diffusivity, which is also the Lewis number. And if we keep in mind a situation with moist air, the Lewis number is pretty much 1, and you need moist air, so you have the two fluids, so the mass diffusivity is defined. So we'll just keep that in mind for this situation. So next we want to simplify a little further over here. The thermal diffusivity alpha is actually equal to the thermal conductivity over rho times Cp. And now this will allow us to get a good relationship between mass and heat transfer. So we plug this into here, we get thermal conductivity over mass diffusivity, rho Cp to this number. So now we can actually set this equal to down here to get our relationship. So now that we know that these are equivalent, you can see some cancellations happen. So that cancels, and we're left with the Lewis relation. So 1 over the density times the Cp is equal to the mass transfer coefficient over the mass transfer coefficient over the heat transfer coefficient. And this is the Lewis relationship. This is a very important relationship, as we can see that we can kind of analyze the heat and mass transfer together, and it doesn't depend on distance of the container of the pipe we're in, and it also doesn't depend on like the Reynolds number, which involves like the speed the fluid's traveling at. We just have this relationship that's independent of all that.